we're on our section today, which my goal is, well, we'll get this done. Section 14.7. We, we are going to be doing maximum and minimum values of a function. We're only going to do it with three-dimensional functions, which means we're going to be doing it to functions that look something like this. Like z coordinate is f of xy. Now, when you sketch a three-dimensional surface that has this format, there are certain shapes that follow. I think of like the hills of England, right? Flowing valleys and hills. You will get shapes. In fact, I'll take it outside of that. You get surfaces where at least on part of the surface you get a hill. And that guy there is called a local maximum, which isn't a surprise. And in some parts of the surface, the shape looks like that. And this guy here is called the local minimum. And you can imagine that over a surface, there may be more than one of these. There may only be a single one. There might only be a local maximum. The surface is just one big hill. There is a third shape that we are after. We want to find where it is, and that shape's called the saddle point, and I'll try my very best to draw it. It looks something like this. And this point here is called a saddle point. Now, it's pretty obvious to look at that and say it's a local maximum. No matter what direction you travel on that surface, isn't that the top of a hill? It's a maximum. And no matter where you travel locally close to this guy, you're always going to head downwards to a minimum. But this shape here, it depends on which direction you are traveling, whether you would think of this as being the top of something or the bottom. What do I mean by that? If I was here on the surface and I was walking to that point there, and then I passed it and I went down the other side, from my perspective, isn't that journey climbing up to a hill and then passing through it and going down the other side? It's like a local maximum in some ways, but not perfectly slow. On the other hand, if I was here and I walked to there and then continued, can you see that that point, as far as this journey is concerned, the dotted green one, isn't that really a minimum? Right, I'm coming down and back up. That shape is a little bit of this, a little bit of that. It's called a saddle point. And our quest is to find where these things are, and we call the points where these happen critical points. And then we have to find out, once we find the critical points for a function, we have to find out which one of these three situations happens. And it will have to be one of those three situations, typically. And the way we do it is by using this thing called the second derivative test. And that's basically a little bit more than half the questions that we're going to do. And then the second half of 14.7 consists of problems. Applications. Okay, so let's get started with one. How do you find critical points? Well, if you look at this shape here, and you wonder what is going on as far as derivatives are concerned, if you slice a shape parallel to the x-axis, you're essentially finding the partial derivative df by dx. And if I slice it right in the middle there, can you see that what you would get is a top of a hill? Its derivative would be 0. So the partial derivative with respect to x is 0. So when critical points happen, you get a 0. You also, if you cut it parallel the other way to the y-axis, you also find that this is true. So critical points are those points where you solve when is the partial derivative with respect to x equal to the partial derivative with respect to y, and that they're both equal to 0. And that's it. So the only places where a local max, a local min, or a saddle point happens is when the two partial derivatives are both 0 at the same time. So let's take an example of a function and let's find its critical points. It's x squared plus xy plus y squared plus 8y. Now, I'm going to do the partial derivative with respect to x. So that's going to get me 2x plus a y plus a 2y, and that's going to get me 0. So I want that to be equal to 0, and I'll call that equation 1. Now I'll do the partial derivative with respect to y. That's going to get me nothing. That's going to get me...
I think the y squared stays y squared, doesn't it?
If you differentiate y squared, well, let's check it. With respect to x, 2x, with respect to xy, and this guy here doesn't exist. If you differentiate that with respect to x, you get 0, and if you differentiate that, you get respect to x, you get 0. Are we good?
Good.
Right. Okay, let's tackle the second one. Differentiate that with respect to y, you get 0. Differentiate that with respect to y, you get x. Differentiate this with respect to y, you get 2y. Differentiate this with respect to y, you get 8. And that also has to be equal to 0. And so we now have two equations. 2x plus y must equal 0, and at the same time, all of this equals 0. So I'm going to use hopefully you can recognize it as a system of two equations. And I'm going to take equation 1, and I'm going to rearrange it and say that y equals negative 2x. I could have solved this by the addition method, but I'm going to do the substitution method. And then I'm going to put that y equals negative 2x into equation 2. So that's how I'm going to solve this system of equations. And what do I have? I have x plus 2y add 8 equals 0. X plus 2 lots of negative 2x add 8 equals 0. X take away 4x. Might as well subtract 8 while we're at it. Negative 3x equals negative 8. And so I get a value that x is positive 8/3. Now, I need to know the y-coordinate that corresponds to that solution. Well, when x is 8/3, which one can we use? This one here. Y is negative twice x, so the y-coordinate will be negative 2 times 8/3, and so y will be negative 16/3. So I can tell you the coordinates of the only critical point in this case. 8/3, -16/3. Now, I could have solved this system of equations in a different way, just to show you, because some of your minds might be thinking along these lines. If I rewrite equation 1 like this, and then I rewrite equation 2 like that, can you see a system of equations? Now, couldn't I have multiplied one of them by -2 and did the addition method and so on and so forth? And can you trust me, you end up with that solution? Just a different approach. So that is how you find the critical points. You find when the values of x and y, the pair of x and y, where the partial derivative with x and with y are both equal to 0 at the same time. Okay, let's try another one. They mostly tend to be polynomials, these questions, because they're so difficult to do otherwise, I guess. Let's see if I can find something interesting. Okay, this one looks a bit different. Let's find the critical points for this function. 2x², take away a 6x, add a 6x, y². Well, partial derivative with respect to x, 6x², take away 6, plus 6y². And I want that to equal 0. I'll call that equation 1. Now, the second one, that's nothing, and you get 12xy, and I want that to be equal to 0, and I'm going to call that equation 2. So in case you think you end up with a system of equations like we did the first time, you don't. This is a pair of equations, but they're not going to be solved anywhere like the first one. I'm going to focus on this equation here. If you tell me that 12xy equals 0, there is a limited number of conclusions I can make. The first conclusion is that x was equal to 0. Would you agree? And I'm going to run with that and see if it generates a solution, because sometimes it does, sometimes it doesn't. So I'm going to assume that x equals 0, and now I'm going to find out what would y need to be for that to happen. Well, if x equals 0, y can be anything you like, because that's still going to be 0. So this is the guy that's going to be important. So 6x² take away 6 plus 6y² equals 0. When x is 0, that's 0. So you've got -6 plus 6y² equals 0. That tells me that 6y² would have to be 6. That tells me that y² has to be 1. And that tells me that y has to be plus or minus 1. Right? So when x is 0, y can be 1, or y can be -1, and those are valid solutions. So here's my solutions: 0, 1, 0, -1. We agree? That's two possible solutions. Now, there is another conclusion that I could have came from this guy. The conclusion I started with is that maybe x was 0, and that's good because it generates two answers. What's the other conclusion I could have made in 12xy equals 0?
Y equals 0.
Okay. Now let's see what happens with that. I'll call that my second conclusion, though it doesn't need a name. Now, if y is equal to 0, x can be anything it likes. So this is the guy that's going to tell me what's going on. And what do we get? We get 6x² take away 6 plus 6y² equals 0. Next thing we get is that 6x² take away 6 plus nothing is 0, because 6 nothing squared is still nothing. 6x² is 6, x squared is 1. Oh, kind of symmetry going on. X could be plus or minus 1. Well, that means 1, 0 and negative 1, 0. There are two more critical numbers. I might have exhausted all possibilities, but I'm going to try one more, which I'm 99% sure isn't going to work. But you know when you don't check something, and 99 times out of 100, it doesn't matter if you don't check it because it doesn't work. The one time that you should have checked it is the one strange time where it does work. So what am I getting at? There is a third conclusion. What would that be? 12xy equals 0. The first conclusion is x is 0 and y can be whatever you like. The second conclusion was y is 0 and x can be anything you like. What's the last situation I haven't really worked on? Shouldn't I check that x equals 0 and y equals 0 at the same time, right? Both of them being 0 might work. Now, does it work for this guy? Sure does, right? 0 and 0, 12 0 zeros works. Now, if I go to the other equation, which is 6xy take away 6 plus 6y squared has equals 0, and I make the assumption that both of these are 0, let's see if it works. Nothing take away 6 plus nothing equals 7 equals 0. It doesn't work. And 99 times out of 100, it never will work. But it's always worth a try just to be on the safe side. And Thomas, you were right, and Kel, you were right, they were both 0. Okay, are we comfortable that there is a process that we're going to do now, which is finding critical numbers? And that's the first part of the process about finding what the local maximum value is, what the local minimum value is, and what the coordinates of the saddle point are going to be. So now I'm going to take you to the second derivative test. The second derivative test says this. If you have a critical point, and let's say its coordinates are a comma b, so that could be 0, 1, 1 minus 1, whatever it is. If you have a critical point AB and you find D, which is the second derivative with respect to x evaluated at AB times the second derivative with respect to y evaluated at AB, take away the second partial derivative f of xy evaluated at AB squared. You find this expression. It's called capital D. And here we go. If D is positive and the second derivative evaluated at AB is negative, so that's 10 and that's minus 2, then you have a local maximum. Now, if D is positive and the second derivative evaluated at the critical number is also positive, then you have a local minimum. If D is just negative, then you have a saddle point. And if D equals 0, scream profusely and throw things at the computer screen. Because if D equals 0, it means we do not know what the heck is going on. It could be a max, it could be a min, it could be who knows. It could just be a flat plane for all we know. And the test is inconclusive. This test is called the second derivative test. You can see from the way the test works, the value of D here, that that there's a lot of work involved in finding local max, local mins, and saddle points. So I'm going to return to, if I can find it at least. Yeah. The first question that we did today was this guy here. Right, remember that guy? And after a fair amount of work, we found out that there's only one critical point. And it had coordinates 8/13 and -16. Right, 8/3, I should say. 8/3 and -16/3. Right, that was our guy. Now, what we need to do what we need to do now is use the second derivative test on that guy. And I've got a lot of bits of paper floating about, which means I'm going to have to go hunting for it. Here we go. So, to be able to find D, we need to take this guy and find its second derivative and evaluate it at that point. That fella evaluated at that point. This guy evaluated at that point. Partial derivative with respect to x. 2x plus y. The second derivative with respect to x is just 2. Partial derivative with respect to y is x add 2y plus 8. And the second guy is what? 2 again. Now the partial derivative x, y. Well, if you take this guy and do them with respect to y, you get 1. And if you do this guy with respect to x, you get 1. So here are all the guys that we need. Now D is this fella times this fella, take away that fella squared. Now the good news is that the guys that we need to use were all numbers. So I didn't need to use the X and Y here, but can you imagine sometimes that might be 2X or that might be Y cubed or something, right? In which case I do a little bit more work. So let's see what D looks like. It's 2 times 2, take away 1 squared, which is what, 3. Now, second part of the puzzle is what is the second derivative equal to? And the second derivative is here, and it is positive. So D equals 3, and this guy is equal to 2. D is positive. This guy is positive. Okay, what is the conclusion then? Local max, local min, or a saddle point at this one critical number?
Local min.
Agreed? Local min. So I know that there is a local minimum, and the coordinates are 8/3, -16/3, which is fine. I can handle that. Now, if the question had been, tell me the coordinates, the X and Y coordinates of where the local min is, that would be the answer. But the question asks us for the local minimum value. So what they really want to know is the value of the function at that point. So that means I'm going to have to plug in 8/3 squared and put the guys in there and put the guys in there and go and put the guys in there. And I'm going to cheat because there should be a nice answer to this. And darn it, there isn't a nice answer to this. Okay, I'm going to cheat. The answer is 42. Can you imagine plugging that in? It's just going to take 5 minutes of horrendous button pressing. But won't you get the answer 17/9 or 42/3 or whatever it is? Whatever that number is, I'm pretending it's 42 just so I can finish this question. You would be able to say there is a local minimum and its value was 42. And that's what you would be putting into WebAssign as your answer. Not the coordinates, but the value of the function at, in this case, that particular point. Are we good? Right. Let's move to the second question that I did today. So that means I can throw away a whole load of pieces of paper, I hope. And the second one that we did today looked like this guy here. Right, that was the second one we did today. And we found out that there was quite a few critical numbers. There were 4 altogether. And we are going to test each one of these to see if there's a local max, a local min, or a point of inflection. So, partial derivative with respect to x is 6x squared take away 6 plus 6y squared. If you do the second derivative, you just get 12x. If you do the partial derivative now with respect to y, what do you get? Nothing, you get 12xy. And if you do y a second time, you get 12x. It's interesting. And then f of xy, well, if you take this guy and do it with respect to y, disappears, you get 12y. Now, d is that guy times that guy, take away that guy squared. Now this guy here is what? 12x. This guy here is also 12x. And this guy here is 12y squared. So what you end up with is 144 x squareds, take away 144 y squareds. And if you want to make it vaguely pretty, you could do that, right? So I'm just evaluating or simplifying what d is equal to in terms of x and y. So what I'm going to do now is plug in each of these values to see what kind of d we get out of it. Let's try our first point, -1, 0. So x and y. D is 144 times -1 squared take away 0 is 144, and that is definitely positive. And what is f of x? X equal to, well, it's equal to 12 times x, and this time it's 12 times -1, which is -12, which is less than 0. So at the point -1, 0, at that critical point, d is positive, and that guy is negative. So that means this guy is a local max. So a little bubble around him. Now, if I try the next point, which is 1, 0, d ends up being positive, and f of xx also ends up being positive, which means at this point, 1, 0, we now have a local minimum. If we move on to 0, 1, let's do 0, -1. D is 144 x squared, take away, well, take away -1 squared, take away 1. It is negative d. That means 0, -1 is a saddle point. And if I do 0, 1, d ends up being essentially the same calculation. It ends up being negative, which means at 0, 1, we have a saddle point. Now, what will that look like when you do your answers in WebAssign? Well, WebAssign looks like this. You have a local maximum values, and then you have a box, and then you have local minimum values, and you have a box, and then you have saddle point, points, and they have a little XY to remind you how you write them. So the way you write your answers is different. For saddle points, you put the coordinates. For local max and local min, you do not put you do not put the coordinates. What you put instead is the value of the function at this point. So this function was 2x cubed take away 6x plus 6xy squared. And if you find its value at -1, 0, you get -2 plus 6 and a nothing, so you get the answer 4. So this local maximum is a 4. This local minimum, well, the same function. And this time we're going to evaluate it at 1, 0, which is what, 2 take away 6 from nothing, so you get -4. And that's the way you would write down the answers to local max and min. Any questions so far about how we find local max and mins using the second derivative test and critical points? Anything that doesn't make sense or you'd like me to talk about? Okay. Would you like me to do one more polynomial? Because they are basically polynomials from start to finish, going through this process of finding critical numbers and then using the second derivative test to see what kind of situation we get at those critical points. Do you want to see one more, or are we good? I need some feedback here, guys.
I'm good.
Good. Okay, I guess you'll find out. Hopefully. It is a consistent process. And so, oh God, give me a few seconds here, get some air. I am fed up with this bloody thing. I am not good at being sick. I am fed up. I do not want this cold, infection, whatever it is anymore.
Yeah, it sounds pretty bad.
Oh, it's just a pain in the butt. That's what it is.
And you have asthma too, right?
I have asthma, which just doubles the thing up. I've
Yeah.
already went through 2 emergency ones. I had to get a new one because I'd used them all up. It's the only thing sometimes it keeps my tubes open. It's a pain in the butt.
I think with these, like remembering the rules is the big part on this one.
Remember that what you need to do is find the partial derivative with x and y, make them both 0 and solve. Because if you can go over the find the critical points, this here is really plug and chug, right? Second derivative, second derivative, second derivative. If you get a number and it's negative, saddle point. If it's positive, use this guy to decide whether it's max or min, and bump, you're good to go. I'm just scanning through it in case there was any that might or might not cause some issues. So here is a situation that can arise, and it's in question 10. So we're about halfway through right now. Here is a function. Nothing at all wrong with this function. Except you're not allowed to use any value of x that you like. You have a restriction D. And the restriction D is written in set builder notation. And it is essentially saying this. That. Now, if you draw what that looks like, it's basically a box. And the values are 1, -1, 1, -1. Does that make sense? And you are only allowed to choose critical numbers inside that box or along its edges, right? So when you come to picking critical numbers, and I'm just going to make this up, let's suppose we find 3 critical numbers, and one of them is 0, 2, one of them is 1, ½ and one of them is 1, -1. Right, let's suppose we did the math, ignored that piece of information and just found critical numbers, and we got 3. Why is that one kicked out the list?
Outside the box.
Outside the box. So you may have solutions that work when there's not a restriction, but if they tell you something is, has to be true, then you have to check all your critical numbers to see whether or not they fit in the box. Secondly, when you put a restriction on what values of X and Y you can use. You just have to trust me on this. But the coordinates of the four corners, those guys, they become possible places for a local min and a local max. Not because there's going to be a hill there, but can you imagine that if you stop at shape, couldn't you have that guy there? Right, there's a surface going on here. But couldn't that guy there be the top of a sort of a hill? So when they give you restrictions, check the four corners as well. Now, in this particular case, did you notice that that one happened to be one of the four corners? Right, so I wouldn't check it twice. So in this case, I would be checking these four guys and 1 comma a half. And then we could do our basic test to see local max and local min. And you can plug the guy in there and plug it in here and see what you get. So I'm just looking, they did a couple of them, then they did examples. So that's what you do if they put a restriction. Kick out numbers that are not inside the restricted area and use corners as other test points. So if the value of this function, all you do is find the value of the function. And if it's bigger, it's a local max. If it's smaller, it's a local min. The only ones that you check the usual way are the two normal critical numbers, and you would do this test on them. These guys would get tested only on what their value was, not what the second derivative test would tell you. Right, so now we are entering applications, and applications, I believe, yep, start at 12. So I'll pick 12 as my start. Well, no, I can't pick 12. 12 is a video that you watch that tells you how to do it. So I'm going to pick 13, which is a similar question. And it says, find the shortest distance from the point 5, 0, -6 to the plane x plus y plus z equals 6. Now, if you want to imagine it, can you imagine that's the plane? And this guy here is the point 5, 0, -6. Then the shortest distance would be that distance there, right? And we are going to find that shortest distance. So how do we go about that? Oh, this is how you do shortest distance ones. This mysterious unknown point, we're going to call it x, comma, y, comma, z. And the distance between 2 points, you use a formula called the distance formula. And it's x take away 5 squared plus y take away 0 squared plus z take away 6. So that's z add 6 squared. And that's called the distance formula. So that's going to tell me what the distance from here to some arbitrary point called x, y, z. So far, so good? Now, I'm going to change the way this function looks. I'm going to leave it as x minus 5 squared. I'm going to call that guy y squared. And instead of z plus 6, I'm going to take this equation and rearrange z to be that way. So what we get is 6 take away x, take away y, add 6 squared. So the function that we are going to deal with is we are trying to find the smallest value of this ugly square root. Now, I could leave it and work on that and think of this as being my f of xy. So I could say the function that we are trying to find the local minimum for is the square root of x minus 5 squared plus y squared plus 12 take away x take away y squared. I could do that, but I'm not going to. I'm going to use a different function. And the only reason I'm using this function is because it does the same job, but it's much easier to deal with. If this function is at its smallest, isn't this guy, which is just the square of it, going to also be as its smallest? So if I can find what value of x and y makes this a local minimum, I will be able to find out what value of x and y makes this a local minimum, and I will have found that magic point that we're trying to get. So, differentiate with respect to x. Well, that guy gets you 2 lots of x minus 5. That guy gets you nothing. That guy gets you 2 lots of 12 take away x, take away y to the power of 1 times the derivative with respect to x, which is another negative 1. So you get 2x take away 10 plus 24 minus 2 times that. So I should actually call that negative 24 plus 2x plus 2y. So it looks like we're going to have 4x, 2y minus 34. And I'll call that equation. I want that to be equal to 0. And I'll call that equation 1. And then I'll do the partial derivative with respect to y. That guy's nothing. That guy is 2y. And that guy is 2 times 12 take away x, take away y to the power of 1 times negative 1. So we have this fella, which is what, 4y, add 2x minus 24 equals 0. And I'll call that second guy. So I need to find a point, x comma y, where this is 0 and this is 0 at the same time. So I'm going to put these together a little bit like this. 4x add 2y is 34. And the other equation is going to be 4y plus 2x equals 24. We'll call them equation 1 and equation 2. Do you see we've just got a system of equations? I can solve this by the addition method. I can solve this by the substitution method. It doesn't matter. I'll get the right answer, but I have to pick a method. And I have to figure one to do. So I'm going to pick, what am I going to pick? What do you want me to do? Substitution or eliminate or addition method? Which method do you want me to solve? Pick a method. They both work.
The easy.
The easiest one. That's always a good choice. I'm not sure in this context which one's the easiest, but I'll try. So I'm going to take 4x add 2y equals 34. I'm going to divide everybody by 2. And then I'm going to rearrange by subtracting 2x from both sides. I'm then going to put y equals 17 take away 2x, and I'm going to put it into the second equation. So the second equation is 4y plus 2x equals 24. So it's 4 lots of this guy plus this guy equals 24. For a 68, take away 8x plus 2x equals 24. Negative 6x. Take that away from that. Oh God in Himmel. I believe the answer is negative 44. And so x is positive 44 over 6, which is what, 22 over 3. Okay. Now, if x is 22 over 3, y will be 17 take away 2x. So that's going to be 17 take away 2 lots of 22 over 3. Actually, I did a quick check and that is right. The y value is, can you trust me? Because I've got it in front of me now, it's 7/3. So I know that there is only one critical number and its coordinates are 22/3, that's x, and 7/3 is y. I do not need to do the second derivative test. And the reason I don't need to do that is if there's only one solution and I've only got one candidate for that solution, it seems reasonable that that is the answer, right? That's the x and y. Now, I know x, I know y. I now need to find out what the z is. And the z belongs to this plane here. So what do we have? We have x plus y plus z equals 6. So x is 22/3, y is 7/3, and z is whatever it takes to make that 6. So that's 29/3 add z equals what? 18/3. So that makes z negative 11/3. So what is the coordinates of the point on the plane that's closest to 5, 0, negative 6? The answer is 22/3, 7/3, negative 11/3. We've done it. Now, if you want to know what that distance is, couldn't you put that 22/3 there, the 7/3 there, and the negative 11/3 there, and just do a normal distance formula? And if you did that, can you trust me? Because they tell me it ends up being 7 over root 3, which has probably got something to do with these 3s here. Any questions about that method, that application at least?
No questions for me.
Okay, and Teresa, you're good. Okay, the question that we just did, 14 is very similar.
Sorry, can I ask you the last question?
Say again?
That last question, what format? How do you put that into WebAssign?
Oh, let me show you what that looks like on WebAssign.
Please, thank you.
So I'll stop, I'll jump over, click on that. So you should be looking at 14.7 right now. Is that what you're looking at, guys?
Yes.
Okay, so that one was, why is that there? Well, that's one of those videos and then it takes you through the steps. Okay, that's fine.
So you just put the coordinates in there?
You just, in this case, you just put the coordinates there, yes.
Okay.
In the one before it, you don't put the coordinates, you actually put the physical distance. So sometimes they ask for, 1, 2, 17, and the other, they want the distance square root of 23. So in 13, they wanted the distance, right? So not the coordinate, but what the distance from that point to the horrible point I just found a few seconds ago. Does that make sense?
Yes, thank you.
Yeah. So in this case, I like this one better because you just write the coordinates down. But in this case, you put the D in, and that's basically the same question as well. So let's move on to application, a different kind of question. Application question 16. It says find 3 positive numbers whose product is a maximum and whose sum is 200. So I'm going to do X represents the first number, the first positive number. Y is going to be the second, and Z is going to be the third. Now I know that they add up to 200. Good. And I'm trying to maximize their product. Okay. So I'm going to take this guy here and rewrite him as X times Y times 200, take away X, take away Y. Because if you rearrange this, you can rearrange and find out what Z is in terms of X and Y, right? So instead of maximizing X, Y, Z, I'm going to maximize X, Y, this guy. I now have the function that I need. And I need a function with only 2 variables in it, or else this thing goes haywire, right? We need to find for what value of X and Y, this guy is a maximum. And that means we're going to find its critical numbers. Now, if we are unlucky and find 2 critical numbers, then we'll have to check which one's the big answer and which one's the small one. If we're lucky enough to find only 1 answer, then that must be the one that we're looking for, which is what I suspect is going to happen. I'm going to rewrite this guy that way, because it's just going to make life a little bit easier to deal with. Now, to find critical points, we find the partial derivative with respect to X and set it to be 0. So this guy is going to be 200y minus 2xy, and this guy is going to be minus y squared. Check that out, looks good. Now if I set that equal to 0, now the second one, partial derivative with respect to y, that guy is going to be 200x, that guy is going to be x squared, and that guy is going to be minus 2xy, and that's going to also equal 0, right? So there's my 2 equations. So I'm going to try and find values of x and y where these 2 equations are equal at the same time. And I have to kind of, deal with what I've got, because nothing is the same, right? If I take the first one, do you notice that there's a common factor of y that I can pull out? I'll call that equation 1. And then if I take equation 2, I can pull out a common factor of x. Okay. So let's focus on this guy. The simplest possible situation would be that y equals 0. Would you agree? Y times this guy is 0, y equals 0. So I'm going to work with that one and see what that does. So y can be 0 and this can be anything you like. Then the second partial derivative is going to be x, 200, take away x, take away 2y, has to be 0. And if y is 0, you get x, 200, take away x equals 0, because 2 nothings are nothing. And that generates the x could be 0. And this one generates x could be 200. So our first set of critical numbers are 0, 0 and 0, 200. Are we cool with that? Now, if I start on this one and I make x equals 0, then I go up and plug here, can you trust me? Excuse me. I got this one back to front. This one is 200, comma 0. But if I switch places, I get 0, 0 and 0, 200. Now I'm going to focus on other possibilities. If we go back to this one, this guy could be 0. And if we look at this one, this guy could be 0. And that one is going to generate yet another critical number. So right now, I've got 4. Actually, 2 of them are the same. For this fella, if you rearrange this equation, you get y equals 200 take away 2x. And if you put that into the second equation, you get 200 take away an x, take away 2 lots of y. So you have 200 take away x, take away 400, add 4x. And you get 3x minus 200 equals 0. You get 3x equals 200. And you will get x is 200 over 3. And can you trust me that you end up with y being 200 over 3 as well? So there is one more possible critical number. I've got 0, 0, that guy, that guy, that guy, and that guy. Since this is the same as that one, I'm just going to ignore that. Now, we already know that z is 200 take away x, take away y. So I'm going to take each one of these candidates and see what happens. If x is 200 and y is 0, z ends up being 200 take away 200 take away 0, and that makes z equals 0. So one of our combinations could be x is 200, y is 0, and z is 0. If I then move to the 0, 0 possibility, z will be 200 take away 0, take away 0, which is what, 200. And so this would generate 0, 0, 200. If we go to the third possibility, which is 0, 200, Z ends up being 200, take away 0, take away 200, and ends up being 0. So you get 0 for X, 200 for Y, and 0 for Z. And the last one that we had was 200 thirds, 200 thirds. And that's X and Y. Let's see what Z would be in that case. 200, take away 200 thirds, take away 200 thirds. And that ends up being also 200 thirds. So we end up with 200 thirds, 200 thirds, and 200 thirds. One of these four guys gives me the maximum product. If you multiply these three together, the product is 0. If you multiply these together, the product is also 0. Multiply these together, the product is 0. And if you multiply these three together, the answer would be that guy and 200 square, 248. 1, 2, 3, 4, 5, 6. There's the answer. The three numbers that would add up to 200, X, Y, and Z, that give you the maximum product is 200 thirds, 200 thirds, 200 thirds. And its product is a ridiculously big number. How about that? Interesting. With very limited information, we can solve quite interesting puzzles. To me, that's quite interesting. Any questions? Let's move on. Let's do a more awkward version of that question, which is 17. Find three positive numbers and the sum of them is 21. And we want to do it so that the sum of their squares is as small as possible. So I'm going to find that guy. That's the sum of the squares. Now, since you tell me that the sum is 21, that means that these are equal to 21, which means I can rearrange. Now I have x squared plus y squared, and instead of a z, replace it with something using x's and y's. So this is going to be our function. And we are going to find critical numbers. And once we find those 1, 2, 6 critical numbers, whatever it might be, once we find them, we're going to plug it into here. And whichever one of them gives me the smallest answer is the minimum, right? Is the guy we're looking for. So the partial derivative of this guy with respect to x. You get 2x, you get nothing, and this is a chain rule, so you get 2 lots of 21, take away x, take away y to the power of 1, times a negative 1. So I'm going to be 42, take away 2x, and then I just did that again, I'm getting tired. Minus times that, so it's negative 42 plus 2x plus 2y. So we are going to be looking at 4x, add 2y, minus 42, and that's our first equation. Got a little bubble around it to try and remind myself where it is. Now I'll do a partial derivative with respect to y, and that'll disappear and we'll get a 2y, and this guy times a -1. And so we get a 2y, -42 again, plus 2x, plus 2y. And now we get 4y plus 2x minus 42 equals 0. That's our second equation. Okay, this one looks a lot less trouble than the previous one, because really all I've got to solve now is a system of equations. There's the first one. I'm just rewriting it again so it's in one place. That guy is equal to 42. And then that guy also happens to equal 42. Let's do the addition method. I haven't done the addition method, and I've just realized something. If you're going to do the addition method, the x's and y's should be above each other. There. So I'm going to multiply this equation by -2 and leave the first equation untouched. So first equation untouched. Second equation, multiplying it by -2. Now I'll add these together. They kill each other off. -6y, -42. That gives me a y value of 7. Oh, nice answer. I'm going to put y equals 7 into any equation I like. So I like that one. So 4x add 2 lots of 7 is going to be 42. 4x add 14 is going to be 42. 4x is going to be 14 away from that guy, 30, 28. Oh, that is too nice to be true. It's also 7. There is only one critical number, 7 and 7. So let's see what the z would be equal to. The z, I forget what that guy was, is way over here. Where did I put you, z? There we go. Z is 21 take away x, take away y. 21 take away 7, take away 7. Oh, that is so pretty. So 7, 7, 7 is the smallest, is the situation that's going to generate the smallest value for x squared plus y squared equals z squared. Now, if the question wants to know what they are, you write this. If they want to know what the smallest value is, you just plug in 7s everywhere, which is what, 49s? And 3 lots of 49 are like 3 lots of 50 take away 3, so the answer is 147. Oh, that is actually a very pretty answer. Compared to the other one, that was really smooth, wasn't it? I mean, if there's only one solution, that must be the solution you're looking for, right? The other one was much messier because there were like, what, 4 or 5 solutions that could be solutions at least, and we had to check all of them. All of them except one ended up being 0, so we did find the correct one, but it's just more work. How are we doing? Okay with that one?
Good.
Good. Right, we're almost done for today. There is one more question that I want to do, but I want to show you that there is a video example of the same type of question. It's one of those, oh God, we've done these in all sorts of places. Remember the boxes without lids question? Yeah. Here's another box without a lid question. Here's a video that you can watch and it takes you through the whole process, which is fine. We are going to do it for question 19. And in question 19, we're told that the box has a volume of 4,096 cubic meters. And what are we trying to generate here? Find a box that has this volume, and it has to have the smallest, the minimum surface area. And does this box have a lid or not? In this question here, they're telling you what it's made from. Okay, so that's fine. It's not quite the same question, but it's similar enough. So now, this is a true statement. You can't adjust this. We are trying to find what the dimensions of a box that would have the smallest surface area if you built it. Now, since the question did not mention that the lid was missing, we will assume that it has a lid, right? Now, if the question did say it had no lid, we would adjust it, but only slightly. Now, the first thing I'm going to do is use the property that the volume is 4,096. Now, if we call this X, and we call this Y, and we call this dimension Z, then the volume is X times Y times Z, and it is 4,096. But what that allows me to do is it allows me to get Z in terms of X and Y, and that's always going to be a goal in these questions. There's going to be a Z there, but we don't want it to stay there, right? We want to find out what Z is in terms of X and Y, so that when we put it together, we now have an equation that only has X's and Y's, and then we can do all the derivative stuff that we've been doing to find critical values. Now, the surface area. Is basically the area. You can tell it's getting to the end of the day. This is my 5th class today, so I'm kind of wore out. What you've got here is the surface area. I'm going to call it f of xy. It's the area of the 6 sides of this shape. The floor is xy, but there's a floor in the center. This side here is xz. There's 2 of them. This side here is 2 YZ. Now, right now, this contains Zs. Replace the Z in its 2 locations by that fraction that I've just written down. So the surface area using only X's and Y's is 2xy. Right. If you double this number, you get 8,192 over y. And this one, 8,192 over x. Are we comfortable about the surface area formula in terms of x and y, right? So this is the guy we're going to differentiate with respect to x, make him 0, differentiate with respect to y, and make him 0. And we're going to hopefully find only a few, hopefully just one, but at least a few critical numbers. Now I'm going to make some assumptions before this has happened. If any of my solutions contain negative x or negative y, I'm going to throw them out because it doesn't make sense in the context of this question, right? So if one of my solutions says x could be -2, I'm going to say I don't care, it's not feasible. Secondly, if any of my solutions say x is 0 or y is 0, I'm going to kick that out for the same reason. Agreed? You can't have 0 width, right? The box would disappear. So let's do the partial derivative of this function. I'm just going to rewrite it while I'm here in this format. So partial derivative with respect to x is going to get me 2y, nothing, and negative 8192 x to the negative 2. And that's going to equal 0. And if I do the partial derivative with respect to y, I will get 2x, take away 8192 y to the negative 2, and that's going to equal 0. So we're dealing with quite weird looking equations here. Next guy. Okay, there's equation 1 written a little bit nicer. There's equation 1 written like that. And here is equation 1. Written like that. So I'm going to rewrite equation 1 in the form y equals. I'm then going to take equation 2. Which is this guy. I'm going to replace y here. And it's going to be really messy and I'm going to have to be really careful. Are we cool? In other words, replace the y by this fraction and square it. Now, although this is a real mess, it has one very nice property. It only has x's in it. So I should be able to, with a bit of luck, solve this. Let's see what it looks like. 2x, take away 8192 over 4096 squared. I'm not even going to turn that into a number. Over x to the 4 equals 0. So that's going to be 2x, take away 8192 x to the 4 over 4096 squared equals 0. Okay. That guy and that guy are going to cancel. What on earth are they going to cancel down to? They are going to cancel as x to the 4 over 2048. Someone do a check on me. 8192 divided by 4096 squared. Do you end up with a fraction 1 over 2048? Because that's what I'm predicting it is.
Yes, you are correct.
God, at this time of night, I can still do math. That's scary. There must be one piece of my brain still functioning. Now, if you have an equation with nothing but x's in it, can't we pull out x as a common factor? Get that? Now, that means there are two possible solutions. Couldn't one of them be x equals 0? But didn't I say at the beginning, if x equals 0 comes up, I'm throwing it out. The other possibility is this is equal to 0. This has got mileage. Oops. If you, and you can solve this different ways. This is the way my brain's working today. If you do that, and you do a little cross multiply, and you take care of the negatives, x cubed ends up being 4,000, and that isn't 4, 2, 2, 16, 9, 4,196. Because someone check that 2 times that guy is 4,196. Because I'm not sure anymore. I think it might be 4,096 now I think about it.
4096. Yep.
Now, doesn't that make x the cube root of 4096? Agreed? Now, is the cube root of 4096 a nice number?
It is in fact.
What is it?
16.
Say again?
16.
Wow. Would you agree that that is too cool to be wrong? Right. I'm very comfortable that x is 16. It's a positive number. It makes sense in the math. Now, what I have to do now is work backwards. What will y be when x is 16? Well, y is 4096 divided by 16 squared, right? X squared, which I believe is also 16, but can you check it?
It is.
And now I need to find out what z is. And z is hidden away somewhere, well, how many pages back here? And z is 4096 divided by x times y. And guess what? That is also 16. Which means that this box, after all that hard work, if you want to make it to have the minimum surface area, you make it 16 by 16 by 16. In other words, you make it a darn cube. Which kind of makes sense, doesn't it? That the most efficient shape with the smallest amount of material for a given volume would be a cube. Now, if this question had the lid removed, this solution would change. And the reason it would change is because this equation here, because there is no lid, would only have a single xy instead of two xy. And that little change makes a big change through the math, right? It won't come out quite as pretty, right? It will come out that there's one solution, and that one solution, I'm not 100% sure what that one solution would look like, but I suspect if you don't use a lid, can't you make the box a little bit taller because you get free space because of lid? I'm assuming you are, I should say flatter. So you might end up with a box that looks something more like this, like 16, 16 and 8. Well, that won't be 16, so 24, 24 and 8, right? It would be shrunk in some way. I suspect that's what you would get if you removed the lid.